Hello everyone, this is Professor Roman. Let's continue the group theory lectures. Now that we've defined the concept of a group and looked at some simple properties, I want to look at some simple examples of groups. And by simple examples, I don't necessarily mean that the groups themselves are simple. I mean that the examples are relatively easy to describe. I will introduce additional groups and go into more details on some of these groups throughout the book. Just to be clear, the process of defining a group from scratch involves first defining the underlying set, then defining a binary operation, and finally showing that the binary operation satisfies the group properties as described in the first definition I gave you. So the binary operation has to be associative, there has to be an identity element, and every element of G, the group has to have an inverse. Once these steps are completed, we can say that G is a group under the binary operation and call that operation a group product. Now, in some cases in these examples, I'm going to define the underlying set and the binary operation and let you show that the group properties hold. The simplest group of all is the trivial group, which consists of a single element, and that has to be the identity. This is called the trivial group. All other groups are non-trivial, and the binary product, there's only one choice. Since there's only one element, 1 times 1 has to be 1. I guess the next simplest group is the group of order 2. This group has to have an identity element and one other element, so the underlying set looks like this. The multiplication table has to be this, otherwise it won't be a group product. So 1 is the identity and A is not the identity. You might ask yourself, why can it not be that A squared is equal to A? And I'll leave that for you to think about. The familiar number systems form groups under the usual arithmetic operations. So we have the integers, the rational numbers, the real numbers, and the complex numbers each form a group under addition, but none of these form a group under multiplication because 0 does not have a multiplicative inverse. The non-zero rational numbers, and I use an asterisk to denote non-zero. So the non-zero rationals, the non-zero reals, the non-zero complex numbers, each forms a group under multiplication. But the non-zero integers do not, because most non-zero integers do not have multiplicative inverses. The positive real numbers, which I denoted by R+, form a group under multiplication, but the negative real numbers do not. This set, which I denote by Z sub n, is the set of integers from 0 to n minus 1, so there are n integers here, which is the reason I use subscript n. This is a group of order n under addition modulo n. Addition modulo n is associative. That requires some proof. 0 is the identity. The inverse of the integer k is n minus k, as you can easily verify. I should say a word about notation. This notation, z/nz, is preferred by many mathematicians over the notation z sub n, and the reason is that when n is a prime p, z sub p is also used for the p-adic integers. But since we're not going to be discussing the p-adic integers in this course, I am using the simpler notation, the one I grew up with, and that I'm more comfortable with. I don't like this notation, it's kind of awkward. This set, Zn star, which consists of all the integers between 1 and n minus 1, less than n, that are relatively prime to n, is a group under multiplication modulo n, and I'm going to leave that for you to check. That would be a really good exercise. When n is a prime number p, then this set is the set of integers from 1 to p minus 1. And this is a very important special case. The order of Zn star is the number of positive integers less than n and relatively prime to n. That is the definition. Now there's a famous function that describes this number. It's called the Euler Fee Function, or the Euler totient function. And it's defined simply by saying that phi of n, phi is a common notation for this function, phi of n is the number of positive integers less than or equal to n that are relatively prime to n. So that doesn't gain us anything until we look at how phi of n can be computed. And it can be, the values of phi of n can be, the values of phi can be computed by looking at two properties. First of all, phi is multiplicative. So phi, if m and n are relatively prime, phi of mn is the product, phi of m times phi of n. And if p is a prime and n is a positive integer, then phi of p to the n is p to the n minus 1 times the quantity p minus 1. I'll leave these for you to verify, or you can look them up on the internet if you want. And these two properties together allow us to compute any value of phi. So for instance, phi of 281,250, that would be the order of this group. First, we factor this number into prime powers. Then we use the multiplicativity of phi to write this. Then we use this formula to give us the value 600. So you probably can guess that I started with this prime decomposition and I worked backwards to get this number. There's nothing special about 281,250, except that it's a pretty large number. So we'll have more to say about these groups, both Zn and Zn star. There are several groups whose underlying sets consist of matrices. The set of all real n by m matrices, and this is the notation we'll use, same notation I used in the linear algebra book, is an abelian group under addition. It's an additive group. The set GLN of R, this is the non-singular n by n real matrices, is a non-abelian group. It's not abelian when n is bigger than 1 under multiplication, and it's called the general linear group of size n. That's why the GL is general linear. The set SLN of R, this is all the real n by n matrices whose determinant is equal to 1, is also a group under multiplication, and that's called the special linear group. As to polynomials, the set R square bracket x of all real polynomials is a group under addition. The set R these are the parentheses, round bracket, x of all non-zero rational functions in the variable x over the real numbers is a group under multiplication. As to functions, if G is a group and X is any non-empty set, it doesn't have to have any structure at all, then this notation, G to the power X, is a common notation for the set of all functions from X to G. And this is a group under product of functions, not composition, product. And the product is defined, you know this from calculus, f g of x is f of x times g of x. The identity is the function that sends every element of x to the identity element of g. And you can check that's neutral for this product. And if f is a function from x to g, then f inverse is the function defined this way. Still from x to g, f inverse of x, you first take f of x, then you take its inverse in the group G. So what's interesting about this example is, again, as I said, x doesn't have to have any structure whatsoever. It does not have to be a group in particular. All the algebraic structure lies in G. G must be a group for this to work, but X can be anything. If X is a non-empty set, then the set of all bijections on X, also called permutations of X, is a group under composition of functions. And I'm going to leave that for you to verify. But we'll discuss this group at great length later in the course, because these groups, known as groups of permutations, are the most important groups in all of group theory. And I'll leave that for now. We'll discuss the reason why later on. Here's an example, a little bit different. The exclusive OR, which is sometimes written XOR, and I'll denote by a plus sign with a circle around it, is defined on the set 0, 1 in this manner. So 0 exclusive OR 0 and 1 exclusive OR 1 is equal to 0. When the two operands are different, the result is 1. And so the result of this operation tells us whether the two operands are the same or whether they're different. As you probably know, a binary word of length n is just a string of n zeros and ones. The zeros and ones are called bits. Now the set, which I denoted by b sub n, of all binary words of length n, is a group under the operation of exclusive OR, applied element-wise. And I'll leave that for you to check. This group has applications in a branch of mathematics known as information theory, also in the theory of error-correcting codes. So, for example, if a binary string U is sent through a communication channel, such as, for example, sent from a spacecraft to Earth, maybe the data is a picture that the spacecraft has taken of Mars or whatever, but the binary word that's received is V because of errors in transmission, then the exclusive OR of the sent word with the received word tells us the positions in which an error in transmission has occurred. And the weight of this word, which is defined to be the number of ones in the word, is equal to the number of transmission errors. Here's an example of groups in geometry. And we'll have, again, a great deal more to say about this later. A rigid motion, or also called a Euclidean motion of the Euclidean plane R2, is a function on R2 that preserves distance. These are also called isometries. And it's not difficult to see that the composition of rigid motions is a rigid motion. The identity map is a rigid motion. The inverse of a rigid motion is again a rigid motion. And in fact that the family of all rigid motions of the plane is a group under composition. And it's called the Euclidean group, denoted by E sub 2 or ISO sub 2, and there are other notations. Now this figure here shows a square sitting in the plane. The vertices lie on the axes, and I put 1 at the top, labeled each vertex clockwise. A rigid motion of the plane that sends the square onto itself is called a symmetry of the square. So for example, a 90-degree rotation clockwise or counterclockwise would be a symmetry of the square. A 45-degree rotation would not be, because the vertex 1, for example, would end up out here in the first quadrant. Reflection across either axis is a symmetry of the square. It's not difficult to show that the composition of two symmetries of the square is again a symmetry of the square. The inverse of a symmetry is a symmetry, and of course the identity map is a symmetry, and so again requires a bit of proof, but the set of symmetries of the square forms a group. And this works under composition. And this works for other regular polygons. And we'll go into that in more detail later on. It gives us a whole family of groups called dihedral groups. The symmetries of the square, for example, form the dihedral group D sub 8. It's a group of order 8. And we'll see that every element of this dihedral group can be written as a composition or product, same thing, of the 90-degree clockwise rotation, which I'll denote by rho, and reflection about the vertical axis, which I denote by sigma. And in fact, the underlying set of D sub 8 looks like this. It's the identity, 90-degree clockwise rotation, 180-degree rotation, 270-degree rotation, flipping about the vertical axis, rotate 90 degrees, then flip, rotate 180 degrees, then flip, rotate 270 degrees, and then flip. That constitutes all of the symmetries of the square. And the product in D8 is completely determined by these three equations. And I'm going to let you ponder why that is now. We'll go into this again in detail, as I said. You can check this by drawing some figures. It's thinking geometrically about this. Here's another group of order 8 that's quite interesting. It's called the Quaternion Group, or the Quaternion matrix group. And we'll study this again in more detail later on. I call it Q sub 8. It has order 8. And it consists of the following 2 by 2 complex matrices and their negatives. So that's where we get a total of 8 matrices. This is a group under matrix product. and I'll let you think about that as well. It's called the Quaternion Group. But because this version of the Quaternion Group, and there will be others that we'll discuss, there's an abstract version. This group has underlying set consisting of a set of matrices. I decided for clarity to call it the Quaternion matrix group. I don't know whether others call it that or not. They may just call it the Quaternion group. As we'll see when we discuss isomorphisms of groups, structure-preserving bijections between groups, that if two groups are isomorphic, then they are essentially, as far as group theoretic properties are concerned, they're essentially the same. And so if one is called a Quaternion group, the other is called a Quaternion group, or whatever the name that fits. And so I just wanted to add the word matrix here just to indicate that the underlying set was consisted of matrices. And I'll let you do the multiplication table for this group and show that indeed we do have a legitimate binary operation on this set Q8. Associativity then will be automatic because we already know matrix product is associative. And here's the identity that's present here. And you'll have to sort out, if you so desire, what the inverses are for each of these matrices. But you have a hint already because I've told you this is a group. So the inverse of A has to be one of these 6 matrices. So you can track it down that way. This example is another example from geometry. It's possible to associate a group with any conic section, any ellipse, any parabola, any hyperbola. This is an interesting example if you're interested in geometry. It involves something called Pascal's theorem. It's not going to be used again in this course, so I'm going to let you read the example on your own if you have the book. There's some more pictures associated with this example. The final example here is let G be a group under a binary operation, which I'll denote by dot, and let H be a group under the operation star. Then the Cartesian product, G cross H, is also a group. We discussed this when we talked about common themes and creating new widgets from old widgets. This is the component-wise product. So you take the product in G of the first components, take the product in H of the second components. And this is a group under this component-wise operation. You need to check the details, the properties. As to notation, I'm going to use a little different notation than you will see in other books. I used this notation first in my advanced linear algebra book, and the reviews were good. People liked this notation, so I decided to stick with it. This is the notation, the X there, that's the notation used for Cartesian product, but to indicate that we have an algebraic structure and not just a set, I put a box around it. This is the usual notation for the Cartesian product. This is the notation for the Cartesian product of two groups as a group. And it's customary also to denote both group operations with the same symbol, usually juxtaposition. So I'm going to drop the dot and the asterisk from now on. This is referred to as the direct product of G and H. And we'll have much more to say about direct products later in the course. A particularly simple and quite useful example of a direct product of groups is this one here. You take the group C2 of A, which consists of two elements, the identity in A, and similarly the group C2 of B, the identity in B. We've talked about this group before. It was an earlier example. And you take the direct product. So you get ordered pairs. 1, 1, A1, 1B, AB. So this is a group of order 4 known as the Klein 4 group, or just the 4 group. It's such a common group. It's referred to as the 4 group. And it was called the Vierergruppe, which is German for foursome, by Felix Klein. So that's how it got the name Klein 4 group. And we will use this group a few times as examples of the behavior of groups. Let's talk now about a family of groups known as the cyclic groups. The simplest types of groups are probably the simplest groups, although the cyclic groups are by no means totally transparent. As we'll see, it's not even always easy to tell whether a group is cyclic or not. We'll also see much later in the course that the cyclic groups form the foundation for all finite abelian groups. Specifically, every finite abelian group is a direct product of cyclic groups of prime power order. And this is a remarkable result. It characterizes for us the finite abelian groups in a relatively simple way. And its proof is going to be probably the most challenging proof in this course. Here's the definition of a cyclic group. A multiplicative group written with multiplicative notation, call it G, is cyclic if it consists of the powers of a single element A in the group. So every element in the group is a power of A. An additive group, G, is cyclic if it consists of the multiples of a single element in the group. In either case, we would say that A generates the group G or is a generator of G. And we'll use various notations depending on the circumstances. This is the most generic notation, the angle brackets around the generator. This notation specifies not only the generator but the order or size of the group when it's finite. And this is what we might use for infinite cyclic groups generated by A. Sometimes we may not even be concerned about the generator. We may only care that the group is cyclic, and so we might write that as C sub n or C sub infinity. And as is customary, we'll use multiplicative notation for general cyclic groups, and use additive notation only when there's a specific reason to do so. All cyclic groups are abelian, since any two elements of a cyclic group are just powers of A to the I, A to the J, and the rules of exponents show us that the group is, that these elements commute, so the group is cyclic. The group is abelian. A common source for cyclic groups is from within other groups, or within cyclic groups, in fact. If G is any group, and A is an element of G, then the set of all powers of A, all integral powers of A, is in fact a cyclic group. In fact, it's a subgroup of G, but I haven't formally defined the notion of subgroup, so we won't worry about that now. And the reason is that the product of G, when it's restricted to just the powers of A, is an associative operation on this set of powers. Here is the equation that tells us that the product is associative. It really comes down to the fact that the addition of integers is associative. A to the 0 is the identity element. We usually write that as 1. And the inverse of a to the k is a to the negative k. The one thing to note here, however, is that it's not necessarily the case that all the powers of a are distinct. And we'll see some example. Well, in fact, we'll see an example of that now. Consider the general linear group G2, GL2 of R. So these are the invertible real 2x2 matrices. And let's look at these two matrices. A little matrix multiplication shows that if we take the powers of the first matrix A squared is this matrix, A cubed is this, and A to the fourth is the identity, which means higher powers of A will just repeat this pattern. And also A inverse is A cubed, so even negative powers of A will be one of these four matrices, either the identity, A itself, A squared, or A cubed. And we can prove that in detail. If we take any integer n, we can write it in this form 4q plus r, where r is the remainder. And so a to the n is a to the 4q plus r, and we write it this way. A to the fourth is the identity. Any power of the identity is the identity, and we get a to the r. So we can always reduce the exponent n, whether it be positive or negative, mod 4, and get an exponent in this range, 0 to 3. So the cyclic group generated by this matrix A has underlying set 1a, a squared, a cubed. The group has order 4. But if you look at the powers of B, then you will see that b squared looks like this. It's the identity, but with a 2 in the upper right corner. B cubed, similar, but with a 3 here. B to the fourth with a 4. And in general, you can prove by induction that b to the n for, well, even for n equals 0 here, b to the n has this form, but if n is not 0, then this will not be the identity. B to the negative n looks like this, again, not the identity. And so all of the integral powers of B are distinct. And so this cyclic group generated by B has infinite order. There's another simple example of cyclic groups. The integers form an infinite cyclic group under addition. Every element in Z, every integer, is a multiple of 1. Similarly, the additive group Zn, remember that's the integers from 0 to n minus 1. Operation is addition mod n. This is also a cyclic group. These groups are additive. We can construct multiplicative versions of these groups, both finite and infinite, as follows. Let's do the infinite one first. It's a little simpler, actually. To construct an abstract, infinite, multiplicative cyclic group, we first need an underlying set. So we take a formal symbol, A, and we take the formal symbols A superscript I, where I ranges over the integers. And I'm choosing this language very carefully. This symbol should be read A superscript I and not A to the ith power. It's a formal symbol. it has no mathematical meaning whatsoever at this moment. So there's no relationship between these symbols. You cannot do algebra. And, for example, a superscript 2 is not a times a, so it shouldn't be called a squared. There's no product yet. All we have is a set with no algebraic structure. So some might use a different notation, a sub I or a of I or something, but I wanted to use this notation for a specific reason, and you'll see why as we go through this example. And it's commonly done this way. So we have our underlying set of formal symbols. Now we define a group product, and we do it as you would expect using the ordinary rules of exponents. So this should be read the product of the formal symbol a superscript I times and the formal symbol a superscript j is equal to the formal symbol a superscript I plus j. It sounds a little weird, but you'll see why, I think, by the time we finish this example, why we're being so careful with the language. Associativity of the product follows from associativity of addition of the integers. And I'll let you go through this. You should be able to do this yourself. It's not that terribly difficult. The identity element is the formal symbol a superscript 0, which we'll denote by 1. And it's common to denote a superscript 1 just by a. The inverse of an element a superscript k is a superscript negative k. And this set, together with this binary operation and the identity inverses, forms a group. This is the infinite cyclic group generated by little a. Now we have to deal with a somewhat subtle but very important notational crisis, you might say. And this is why I've been so careful with the language. This expression has two meanings now, because we've established that we have a group. It is a formal symbol with no intrinsic meaning. It just sits there as a formal symbol, but the group, it's also the group product of k copies of the formal symbol A, of the element A, of the group. So it has two meanings. Fortunately, however, the definition of product applied several times, k minus 1 times, shows that the product of k copies of A is in fact equal to the formal symbol A superscript k. So now we can say A to the kth power. A to the kth power is the product of k copies of A. A superscript k is the formal symbol, the element of the group, but they are the same. Or probably better to say they are equal. I bailed out of that by saying they coalesce. Okay. And if this wasn't the case, we'd be in serious trouble here, because a superscript k would have two distinct meanings, and we wouldn't know. It would be bad news. Okay. As to finite cyclic groups, we can do pretty much the same thing. The underlying set, if we want a finite cyclic group of order n, then the underlying set will be a to the 0 through a to the n minus 1. Again, formal symbols with no intrinsic meaning. There's no product here yet. Again, we'll let a superscript 0 be 1 and a superscript 1 be a, as everybody does, and define the formal product of these symbols by a superscript I times a superscript j is equal to a superscript I plus j mod n, because this exponent must be in this range 0 to n minus 1. And as with the infinite case, we will have a cyclic group of order n, and I'll let you check the various properties. Notice in particular A inverse is equal to a to the n minus 1. So that's, from this we can get all the negative powers of A. And again, we don't have that, we can resolve that ambiguity, potential ambiguity, the same way. So we don't have any issues with the interpretation of A superscript k as being the product of k copies of A. There is one other issue that comes up here that doesn't come up in the infinite case. What if the integer k in A superscript k is not in this range? Well, then this expression is not one of these expressions. So it's not a formal symbol in the group. But because this is a group, this does make sense still as the product of k copies of A. And that works even if k is negative. I should have said that earlier. If a to the negative 4 is the product of 4 copies of A inverse. Okay. So our definition of product implies that A superscript k, or this now I can call A to the kth power because that's what it is this element in the group. It's A to the k mod n. Okay. This in fact holds for all integers. Even if k is in the range from 0 to n minus 1, then mod n doesn't do anything, and this is just an identity. So if we have any two integers j and k, we can take this product, a to the j times a to the k, and if you work through the details reducing mod n, you will get a to the power j plus k. So this is rather obvious. You have the product of j copies of A and k copies of A. That's the product of j plus k copies of A. But this is a little more formal way to express it. So we can feel free to do algebraic computations in this finite cyclic group using any integral powers of A that we want without worrying about any issues. So for example, in the group C6 of A, which is the set of powers of A from 0 to 5, we can write things like a to the 24th times a to the negative 10 is a to the 14th. Everything is fine. And if we insist on having the result be an actual element of the group, that's probably not good terminology, but if we insist upon the result looking like one of these, all we have to do is reduce a to the 14 reduces to a squared. There's only a small price to pay for this ability to use any exponent, and that is that, of course, an individual element of the group has many representations. So in this case, for example, a is equal to a to the 7th, equal to a to the 13th, a to the 19th are also negative powers, and so on. But that's not a big deal. Okay. The point here really is that you don't have to reduce mod n every time the exponent falls outside of the range from 0 to n minus 1. you can save the reduction mod n of the exponents till the very end, or not do it at all. Let's talk about generators in cyclic groups. A non-trivial cyclic group has more than one generator, always. If A generates the group, then so does A inverse. And, well, I should say, assuming these are distinct, A and A inverse, then that will be two generators. For infinite cyclic groups, these are the only two generators, because no other power of A to the k, can generate the group. You can't get A by raising A to the k to a power. And here are the details. If A to the k to the n, or in other words, A to the kn, was equal to A, that would imply, that's equivalent to saying kn equals 1, because in an infinite cyclic group, all the powers of A are distinct. So kn would have to be 1, but k and n are integers. If their product is 1, then they're either both 1 or they're both negative 1. So in particular, k is either positive 1 or negative 1. As to the finite groups, things are more complicated. So let's consider first this finite cyclic group C5 of A. This group's generated by A, obviously. It's also generated by A squared, which, by the way, is not A inverse. And it's easy to see. You just take the powers of A squared and you'll get every element in the group. As a matter of fact, and you can check this if you're of a mind to, every non-identity element here, A squared, A cubed, A fourth to the fourth, they all generate. Each one generates the group. On the other hand, if we look at C4 of A, the powers of A squared are 1, A squared, and when you get to the second power, you're back to 1. All you're going to get from the powers of A squared are A squared and 1. So A squared does not generate this group. A cubed does generate it. So we'll return to this question later on when we talk about cyclic groups more carefully. But what we're going to see is what you might suspect is the case for finite cyclic groups, and that is for Cn of A, the generators of this group are precisely the powers A to the k for which k and n are relatively prime. So we'll prove that later on. The final comment I want to make about cyclic groups at this time is something I alluded to earlier. Sometimes cyclicity is hard to identify. So even though cyclic groups seem relatively simple, it can be sometimes very difficult to tell whether or not a given group is cyclic. In an earlier example, 2.5, we defined this multiplicative group, Zn star. It is all the integers in Zn, so it's the integers from 0 to n minus 1, that are relatively prime to n. If you remember, we said we talked about the order of this group. It's given by this Euler Fee Function. It is possible to prove, although with quite a bit of difficulty, that Zn star is cyclic if and only if n equals 2, 4, p, a power of p, or twice a power of p, where p is an odd prime. And that's sort of remarkable. There must be something special about these particular n's such that this group is cyclic, if and only if n has that form. Let's look at an example. If n is 5, z5 star is 1 through 4. Because 5 is prime, all these numbers are relatively prime to 5, and those can be written as powers of 2, so this group is actually the cyclic group of order 4 generated by 2. On the other hand, if n is 15, so that's 3 times 5, it does not fit this pattern. 5 does fit the pattern because e can be 1 here. z15 star are these numbers. These are the only integers between 1 and 14 that are relatively prime to 15. If we take powers of these elements, and there's a lot to do, you could do it in Excel or something, you can see that none of these generate the entire group. So here are the powers of 2, for example. And you only get 1, 2, 3, 4 different integers that way. So this is not a cyclic group. I'm not going to prove this result in the book because it is a little bit, it would take a little bit more technique than we're going to develop here. But I will prove for you much later in chapter 7 that if n is a prime p, that zp star is cyclic. Okay. This should be for an odd prime. Well, actually, I can do it for an even prime as well, because this is just prime, so it'll cover the case 2 as well. So we'll do that also. So that's the best I'm going to do in this course, because this is quite tricky.